Welcome to the podcast, Koala Reading AI. I am your host and the voice behind the text-to-speech model. Get ready for an exciting journey through the world of computer vision. In today's episode, we have fascinating papers to discuss. Let's begin with a brief overview of each one. Paper 1. Fabric. Personalizing diffusion models with iterative feedback. The paper proposes a method called Fabric for generating images that closely match human preferences, and it outperforms standard stable diffusion models in terms of image quality and diversity. Paper 2. CoTracker. It is better to track together. CoTracker is a new paradigm for long-term tracking of points in videos that outperforms the current state-of-the-art in point tracking on various benchmarks and produces tracks which are qualitatively cleaner. Paper 3. Meta-transformer, a unified framework for multimodal learning. The paper explores the potential of a meta-transformer architecture to process multiple modalities and achieves promising experimental results. Now that we have an overview of these exciting papers, let's take a deep dive into each one. We'll explore the abstract methodology and key results of each paper. Paper 1. Fabric PERSONALIZing diffusion models with. Abstract. The paper proposes a new approach called Fabric, personalizing diffusion models with iterative feedback for generating images based on user preferences expressed during multiple rounds of generation. The approach is built upon a fine-tuned, stable diffusion, 1.5 checkpoint, and further enhanced by applying it on top of the low-rank adaptation, LoRa, of stable diffusion, 1.5 based on human preference score. The proposed method is compared to standard stable diffusion models, and the results show that Fabric outperforms the baselines in terms of generating images that closely match human preferences. Method. The proposed approach, Fabric, is designed to incorporate iterative feedback gathered over multiple rounds to generate personalized images. The approach is built upon a fine-tuned, stable diffusion, 1.5 checkpoint, and further enhanced by applying it on top of the low-rank adaptation, LoRa, of stable diffusion, 1.5, based on human preference score. The approach generates images based not only on text prompt, but also on user preferences expressed during multiple rounds of generation. The approach collects the desired evaluation metrics for the generated batch at each round and uses these values to perform quantitative comparisons with the baselines. While Fabric may add images from each round as feedback to future rounds, the baselines do not have a mechanism to incorporate feedback into future generations. Results. The evaluation of two versions of Fabric in the study shows that the proposed approach outperforms the baselines in terms of generating images that closely match human preferences. The first version, referred to as Fabric, utilizes the methodology outlined in the paper and is built upon a fine-tuned stable diffusion 1.5 checkpoint. The second version, named Fabric plus HPS LoRa, further enhances the Fabric approach by applying it on top of the low-rank adaptation, LoRa, of stable diffusion 1.5 based on human preference score. The study opted to include the Fabric plus HPS LoRa version in the evaluation due to its proven ability to generate images that closely match human preferences. The proposed approach has potential use cases in various fields, such as personalized image generation for social media, e-commerce, and advertising. The approach innovates on the existing stable diffusion models by incorporating iterative feedback to generate personalized images that closely match human preferences. Paper 2, CoTracker. It is better to track together. Abstract. CoTracker is a new paradigm for long-term tracking of points in videos. The method simultaneously tracks groups of points and thus learns to account for their correlation. Additionally, training through an unrolled temporally sliding window mechanism allows the model to generalize to long video sequences. Our method outperforms the current state-of-the-art in point tracking on various benchmarks and produces tracks which are qualitatively cleaner. Method. The CoTracker method is based on a deep neural network architecture that is trained to track points in videos. The network takes as input a sequence of video frames and outputs the positions of the tracked points in each frame. The key innovation of CoTracker is that it tracks groups of points simultaneously, allowing the model to learn the correlation between the points and improve the accuracy of the tracking. The method is trained using an unrolled temporally sliding window mechanism, which allows the model to generalize to long video sequences. The network is trained using a combination of supervised and unsupervised learning, with the supervised learning component providing ground truth labels for the tracked points and the unsupervised learning component encouraging the model to learn to track points in a self-supervised manner. Results: CoTracker outperforms the current state-of-the-art in point tracking on various benchmarks, including the Kitty, Mott Challenge, and Waymo datasets. The method produces tracks that are qualitatively cleaner than those produced by previous methods, with fewer errors and less drift. CoTracker is also able to track points and their visibility more accurately than previous work, supporting the intuition that long-term tracking of points in groups is beneficial to single-point models and to dense but short-term optical flow methods. CoTracker has a wide range of potential applications, including object tracking in surveillance videos, motion analysis in sports videos, and tracking of vehicles in autonomous driving scenarios. Paper 3. Metatransformer, a unified framework for multimodal learning. Abstract. In this paper, we introduce the Metatransformer, a novel architecture that can process multiple modalities of data, including images, natural language, point cloud, audio spectrogram, video, infrared, hyperspectral, X-ray, IMU, tabular graph, and time series data. The Metatransformer is based on the transformer architecture and is designed to handle the challenges of processing multiple modalities of data. We demonstrate the potential of the Metatransformer on various datasets and show that it outperforms existing methods in several tasks. Method. The Metatransformer is a transformer-based architecture that can process multiple modalities of data. The architecture consists of a set of encoder and decoder layers, where each layer is composed of multi-head attention and feed-forward neural networks. The encoder layers process the input data, while the decoder layers generate the output. The attention mechanism allows the model to focus on relevant parts of the input data, while the feed-forward networks enable the model to learn complex relationships between the input and output data. To train the Metatransformer, we use a pre-training approach that involves training the model on a large data set of diverse modalities. We then fine-tune the model on specific tasks using smaller datasets. We evaluate the performance of the Metatransformer on various datasets, including ModelNet 40, S3, DIS, and ShapeNet Part, and show that it outperforms existing methods in several tasks, including classification, semantic segmentation, and object part segmentation. Results. Our experiments show that the Metatransformer is a powerful architecture for processing multiple modalities of data. We demonstrate its potential on various datasets, including text, image, point cloud, and audio. For example, we show that the Metatransformer can accurately classify images, segment objects in point clouds, and generate captions for videos. We also demonstrate the Metatransformer's ability to handle multimodal tasks, where inputs from multiple modalities are used to perform predictions. Overall, our results show that the Metatransformer is a versatile and powerful architecture that can handle the challenges of processing multiple modalities of data. Its ability to handle diverse modalities of data makes it a valuable tool for various applications, including computer vision, natural language processing, and robotics. The Metatransformer is an innovative approach that has the potential to advance the field of machine learning and computer vision. Thank you for listening to Koala Reading AI. Hope you had fun.